We already finished the section 2 in these lectures, and I believe you have some idea about what's the difference between the equilibrium state and steady state. And also you can formulate the diffusion equations in steady state and non-steady state. And in order to solve, and by solving this diffusion equation in steady state, you can get the concentration profile of your interesting diffusing atoms along your materials, and it will be only a function of location. And in non-steady state, as we know, the concentration profile will change with location and time. So after solving this diffusion equation, you will get the concentration as a function of location x and the time in your materials. So in the section 3, I believe it's the most important part in these lectures. We are going to show you how to quantitatively describe the flow process. So in these sections, we are going to show you how to describe the flow process that will be very important in kinetics process. First of all, I will suggest you to identify how many driving forces involved or apply in your system. And this driving force will drive what kind of flux through your systems or materials, and this flow process definitely associated with some the entropy production. Can you have idea the entropy production rate? Because kinetics actually is a dynamic process, right? So if you want to compare this system or this material system, the process is fast or slow. So definitely we should have an indicator in this. So what kind of indicator to describe this kinetics process is fast or slow? Here we are going to introduce the term we call the entropy production rate to describe the flow process. So how to describe the flow process? As we mentioned, first of all would be the flux of physical entities included. Probably can be the heat flux, mass flux, and the charge flux. Heat flux and the unit for the flux actually is numbers per area and per time period. So for the mass, like for example, like diffusion in materials, so you can the flux, atomic flux will be the number of diffusing atoms going through the unit area and unit time period. And for the heat flux, probably is not the number, it's like the energy, because heat is the energy, like the unit to describe the heat will be the energy. How much energy flow through a specific area per unit time. And for the charge, probably it's like if you are talking about the electrical current, then we can describe something like a current density. How much current density going through this specific area per time. And as long as you know you have a flux, definitely there's a driving force to drive this flux. So the there are three common use driving force in our material system. To drive the mass transport usually will be the chemical potential gradient. The driving force will be the chemical potential gradient. To have a heat flow, the driving force usually is a temperature gradient. To drive the current going through your materials, the driving force will be the electrical field, or you can you can say probably it's an electrical potential gradient can serve as a driving force to drive the current flow through your materials. So next will be the inertia of the system. Some people will call it as transport resistance or inertia of a system or transport mobility, but it is much related to the intrinsic property of materials we are talking about in our systems. So for example, like if there's a mass transport or diffusion happening in your material systems, so the transport resistance probably will be the diffusivity of these materials. And if the flow process is involved in heat flow, which material property will affect the heat flow in your material system? Usually, the first property probably come up in your mind will be the thermal conductivity kappa. And if there's an electrical flow, a current density flow through your materials, so which intrinsic properties will affect this electrical flow, which we always call it is a transport resistance or inertia of the system? Probably you will say, oh, is that electrical conductivity? Yes. So diffusivity, thermal conductivity, and electrical conductivity would be the inertia of a system or the transport resistance to affect the flow process. So we still need to have this information to well describe the flow process in kinetics. So any universal equation can help us to correlate the flux, driving force, and the inertia of the systems. That's what we are going to talk about. So which energy factor is best best to describe this flow process? Because actually in previous slide we talked about lots of different energy state functions, but however none of them is suitable to describe the flow process. Some people may ask, why? So if you take a look at if we take a Gibbs field energy as an example, the change of Gibbs field energy over time, then we can find that there are 3 parameters will contribute. So you need to sum up. The first one is related to entropy times the partial temperature, partial T, and the second term will be the volume times the change of pressure, the change rate of the pressure, right? And the third term will be related to the change rate of the chemical potential. So because you need to sum up these 3 terms, so it's very difficult to us to know the dg over dt is a positive or negative. After you sum up, you need to sum up each term. Otherwise, it's difficult to you to determine this term is positive or negative. So to simplify this, our textbook provided the other way to well describe the flow process is how about we use the entropy production rate. Because entropy, doing any irreversible process, entropy always increase. So how about if we compare the energy production rate between different systems? Probably is a better choice. So in our textbook, they got a beautiful equation, which is absolute temperature of the system times the entropy production rate per volume. This is a production rate per volume and equals to the flux times the driving force. So some people will ask about, are you sure we can we can apply this equation to any flow process. Can we do that? So following slides, we are going to give you 3 examples, included the heat flow process, electrical flow process, and also the mass transport process to demonstrate that this equation really can well describe the flow process. Okay, that will be, so we will introduce that in following slide. And by the way, some people will say, oh yes, this equation looks combine the flux, driving force, and in. Oh, professor, how about the intrinsic material property? Where are they actually? The intrinsic material property is this effect already embedded in the flux term. As you know, if we apply the same driving force on different materials, the flux already definitely different due to what? They do have different intrinsic material properties. So this flux term already give us some information about the intrinsic material properties. Okay, so let's move to the first one. Is we call the, because we are going to show you 3 cases, right? So the first one is the entropy production rate in heat flow process. So now we consider that we have 2 chambers at T1 and T2, and the T1 is harder than T2. I mean, T1 is larger than T2. That means this is hotter and this is colder. And we connect these 2 chambers with a metal bar. And as you know, T1 is larger than T2. So after connected these 2 chambers, there must be a heat flow from T1 to T2, and we call this a delta Q. Okay, now we assume the delta Q flow from T1 and T2, and the change in entropy production rate in 2 chambers can be formulated as to be what? So based on the second law of thermodynamics, you can simply write down the entropy, I mean the entropy change in chamber 1 can be expressed like minus delta Q over T1, right? And minus because T1 lose delta Q. And for the T2 chamber, it gain or gate the delta Q, so it's a plus delta Q over T2 because the temperature here is at T2. So the total entropy change for the system, you need to sum up the net change in entropy. Just simply sum up the entropy change in chamber 1 plus entropy change in chamber 2. Then you got this result. And delta Q is positive, T2, T1 is positive, and T1 minus T2 also positive because T1 larger than T2. So the net entropy change is positive, right? So let's tell you that the heat flow process increase the entropy of total entropy of the system. So also the heat flow resulted the increase of entropy. So that will cause the entropy production. Okay, so some people will probably ask, yes, now you only have delta S is a net change in entropy. Can you demonstrate and show us how the equation we derive, I mean the equation shown in previous slide really work in heat flow process? So before that, we need to define some parameters here. We assume if the metal, this metal bar, the metal area is A, and the length here is L. Okay, so the entropy production rate, we just show you like the total entropy generate in this system per rate, so it's divided by time period, and also the volume. So volume will be the A times L, right? The volume of the metal. So you can simply ds net, you just copy this one, right? T1 minus T2, T1, T2, and the time, and also the AL, right? Okay, and here, okay, just separate them. Delta Q, delta T, and A, T1, T2. Then we put L here. And what we have is T1 minus T2. Okay. So what's this mean? Is heat. The change of the heat per unit time period per area. So actually this is heat flux or heat flow, right? J sub capital Q. And the rest of part is T1 times T2. So we, in order to simplify them, so probably we can, if the questions, if the problems didn't give you what is T1 and T2, so probably you can make some assumptions. Okay, so here, if just for example, if the questions tell you that T1 times T2 equals Tm squared, that's just implying that the T1 and T2, there's no big difference between T1 and T2. Okay, so we can put here the Tm squared and T1 minus T2, and we can. And what's this term? Is a temperature gradient, minus temperature gradient, because the heat flux is going this way, right? So it's a T2 minus T1 divided by L is also the gradient. But now here is T1 minus T2, so I put it minus temperature gradient. Okay, so let's keep, so, and this is entropy production rate. So I move 1 Tm here and left 1 Tm here is minus temperature. Okay, so we successfully got the equation. We just want to show you is well, here we tell you it's like entropy production rate times the temperature term equals to what? Flux times the driving force. Just remind you, a driving force in heat flow process here is related to a temperature gradient. Yes, but minus temperature gradient over Tm. Is that okay to you? Some people will probably will after class, actually some people ask about if we don't the questions didn't give you the relationship list here. Oh, sorry. So what's the temperature we should use in here? What's the temperature here will be the better temperature? I would say, because now usually in this case the size for the heat chamber should be the same, right? So I would say it should be like the average of T1, T2 will be the suitable to describe T here. But if if the questions provide you extra information or relationship between T1 and T2, or the final temperature or the average temperature of their systems, So then that depends on the questions. But if there's no any extra information, I would say you just average the T1 and T2, then you can substitute this T. Okay. The second case we are going to introduce you is the electrical flow process. Can we also demonstrate that the equation we just derived from previous slide can also apply in electrical flow process? So now we have a metal bar here, the yellow metal bar, and we connected this metal bar to the battery, something like that, which can provide the electrical field or electrical potential gradient. And we assume this end, the electrical potential is V1. And at this right end, the electrical potential is V2. And we assume V1 larger than V2. So there must be a current flow from V1 to V2. And this electrical current flow through this metal bar. That gives you some idea, right? That definitely generates some heat. So this heat, we also call it as a Joule heating. And can you simply calculate the power generation rate for this Joule heating? Yes. P equals to IV, right? I times V, or I squared R, right? So it's based on the Ohm's law. So we can simply formulate this, the power generation rate per volume can be expressed like, because this power generation rate is P, so it's IV or I squared R, and you just copy the AL, is a volume here. Oh, so just remind your resistance is R, and the cross-section of this metal bar is A, and the length is L. Okay, so based on this, A times L is a volume of this metal bar. So you just separate I squared R. You put one I here, and IR, what's the IR? Is delta V. So will be delta V, because the electrical currents flow this way, so it's V2 minus V1. Right? Okay, so the gradient here will be the V2 minus V1. Okay, so anyway, IR will be, the delta V is V1 minus V2, and divided by L, because we put A here, L here. So I over A is a current divided by area, is what we call the current density here. And the V1 minus V2 here over L can be considered gradient of electrical potential. But just as I mentioned before, the current go through this way. So the if you write down, should be the V2 minus V1, right? So would be the minus electrical potential gradient, because this is V1 minus V2. But here we should, because the current is go this way, so if you take the gradient, it should be V2 minus V1 divided by L is minus electrical potential gradient. Okay, so now we got the power generation rate per unit volume. Then in order to demonstrate the equation, we show you like entropy production rate times the temperature equals to flux times driving force. So we try to we use the same term here, just move the volume to the up here. And as you know, delta Q is equals to what? T delta S. So we put T delta S. Now we grab the entropy term here. So T times delta S divided by volume, and the delta T here. So we got the temperature times what? Entropy production rate per volume. So it's the sigma dot. So these are identical. So finally we derive like this equation is temperature, absolute temperature times the entropy production rate equals to the flux. Here is the current density times the driving force. The driving force in this system is minus electrical potential gradient. So this is driving force when we have an electrical flow here. So this result also tell you that any electrical flow will cause the entropy production. Okay, so next, the third example will be the diffusion in solid materials. So will be the concentration gradient or chemical potential gradient cause the atomic flux, right? Cause the mass transport. But before we move to our questions, so you need to have some background information knowledge about what's the relationship between the chemical potential mu and the composition x. So now you consider an alloy with a composition XA. XA is atomic fraction. XA, so it's located between the 0 to 1 at constant temperature and pressure. So the composition of B will be 1 minus XA, right? Okay, then can you formulate the total free energy of this AB alloy? Yes, you can express like Na, the number of A atom in this AB alloy, times the chemical potential of atom A, plus the number of atom B times the chemical potential of B atoms. And also you can express like, because we want to get what's the mu A and mu B, so the other way to get this can be expressed like this, is mu A or Na times mu A0. Mu A0 actually is a chemical potential of atom A in pure A materials, and plus the Nb number of atom B times the chemical potential of atom B in pure B materials. Then you just need to, because this is a pure A and pure B, you sum them up, right? But now it's alloy, so you need to minus the entropy term, the mixture. During the mixture to form this alloy, there's some energy loss, right? Or decrease in the total energy of this alloy. So you need to minus the mixed entropy term, which is minus T delta S mix a mixture of A and B atoms. So sometimes you can consider G equals H minus T delta S. Minus T delta S is a mixture entropy term. So what's the delta S mix? So you can express like this is equals to Boltzmann constant K log omega. Omega is a possible configuration or possible combination of A and B atoms. So we can express like the factorial Na plus Nb divided by factorial Na factorial Nb. If the N is very large, then you can do this approximation, and you just plug it, just substitute this information here, then you can get the entropy. Delta S mixture can be expressed like minus K Na log Xa plus Nb log Xb. So you just use this term and substitute this term. Then you can rewrite the Gibbs free energy can be expressed like this. But so far we just get the total energy of this AB alloy, right? But what we are interested in is how to we want to correlate the chemical potential mu and X. That means we try to link the mu A and Xa. So what's the mu A? Mu A is if you ended one atom, how much total free energy increase? So it would be mu A at Xa is a partial GAB partial Na, right? This is a definition for chemical potential A at XA. So you ended one atom, A atom, and how much total free energy increase is a definition for mu A XA at XA, right? So you partial this term with Na. So just this one is mu A0. This is no mu A, so just drop this term and just this term. So your KT partial Na, so KT log SA. So now we successfully get a relationship between the chemical potential of A XXA and its composition XA, right? And based on this, as you know, XA is between like 0 to 1, so log XA is negative. So some people will rewrote it as a minus TSA bar. SA here is we call it as a partial atomic entropy. And this is negative term, and minus, so TSA bar, so SA bar, this partial atomic entropy must be positive. And partial atomic entropy be precisely is similar with the chemical potential is like if you ended one A atom, how much entropy in total entropy increase in your system, we call it a SA bar. Okay, so here we got to give you a short summary is, if we decrease the composition of atom A, then we got the entropy, partial atomic entropy increase, and also this is, if we decrease this one, then we got the chemical potential decrease. So here you have some summary that the chemical potential of atom A, if you change the chemical, if you change the composition of atom A in your materials, then the chemical potential of atom A changes as well. If you decrease the composition of atom A, then the chemical potential decrease in the meantime. So the chemical potential of atom A changes with composition. Okay, so in the follow this concept, if you increase the composition of atom A in your alloy, the chemical potential of atom A increase in the meantime. Now we have this relationship between the chemical potential and the atomic fraction of atom A. So now we'll move to our third example is the entropy production in the mass flow process. As we mentioned, the mass flow process. So here, the example here is we have AB alloy, and with two ends, we do have different composition of atom A. At this this location, the XA1 is higher than XA2. That means more A atoms located at this end compared to this end. So, based on your knowledge, you know there's definitely atomic flux from location 1 to location 2, because here we have more atom A, right? And we assume the cross-section area here is A. So atomic flux usually just imply that there's definitely a chemical potential gradient or difference along, in this material. So if you grab like the chemical, if you write it down as a chemical potential difference, delta mu would be, because the atomic flux is this way, right? So XA2, mu A XA2 minus mu A XA1. So we can know the chemical potential difference between these two ends. And based on previous slide, you know mu A XA2 can be expressed as mu A0. That means the chemical potential of atom A in pure A metal and plus the KT log XA2. So we just substitute this here and minus this term. So this one mu a xa1 also have mu a0, right? So it's equals to mu a0 plus kt log xa1. So drop the same term out. So the only thing you left is this term, right? So kt log xa2 minus kt log xa1. So because the xa2 is larger than xa1, so xa2, oh sorry, the xa2 is smaller than xa1, so this term will be negative. So the chemical potential difference will be negative. So it's reasonable, right? Because this kind of kinetics process decrease the total energy of this system. So delta mu should be negative. And also some people will can be returned, can be expressed like T minus delta SA bar. Okay. And based on this term is negative, so delta SA bar will be positive. So we want to correlate the equation we derived for you. So the production of entropy, production rate per unit volume, and the absolute temperature, we just write it down. So it's the temperature times what? Entropy production rate per volume. So entropy production, total entropy production should be found here. So during this diffusion process, total entropy production is what we know, the one entropy, entropy production for one atom, and we sum up the total number of A atom. So this will be the total entropy production rate per volume. Okay, so we just simply, and also you know this term minus this term is like a delta mu, right? So it's T delta SA bar is minus delta mu, so it's minus delta mu, and we left the rest of the term, and we just try to separate them. Delta mu and L, we just put it together, and this one, and this one just grab here. Why? Because this term is what? The number of the A atom per unit area per time period. So this is atomic flux, and the rest of term here is what? Delta mu over L, as L is here. So it's a temperature minus electrical potential gradient. So it's an electrical potential gradient. So we successfully find out like temperature times the entropy production equals to flux driving force. So for the mass transport or diffusion in solid materials, the flux is atomic flux. It's how many atoms flow through specific through the unit area and per unit time. So it's atomic flux, and driving force can be expressed like a minus chemical potential gradient. Okay, so mass transport also result in the entropy production. So it's we successfully confirm that this equation we derive can be used in mass flow process. Okay. Let's give you a short summary for the entropy production in flow process. So the rate of entropy change instead of the free energy change will be used to characterize or quantitatively describe the irreversible flow process in kinetics. And we also demonstrate that the heat flow, electrical flow, and mass transport will lead the production of entropy in your interesting systems. So you can use these beautiful equations, the absolute temperature times the entropy production rate per volume will be equals to the flux times corresponding driving force. So for different material systems, you can, first of all, you can identify the flux and the driving force applied in this system, and also the working temperature. Then you can you can easily get the entropy production rate per volume. For the heat flow cases, if you can directly calculate the total entropy change, then you can just divide the time period and the total volume in your during your observation time. Then you can get what's the entropy production rate for heat flow process. And if for the case is that the electrical flow process, then you can measure the electrical current flow through your materials times the electrical field applied in these systems. Then you can get the entropy divided by temperature. Then you can get the entropy production rate per volume for this electrical flow process. And for the mass transport or diffusion in solid materials, you can as long as you know the atomic flux and just easily times the minus electrical potential, minus the chemical potential gradient and divided by temperature, then you can know the entropy production rate per volume for your material systems. Okay, so today we just ended here.